Hello dear students, I'm Rana Kumar, your physics faculty, and a very warm welcome into this session in which we will be discussing problems of the paper AIATS PLUS 2025 Phase 2 Mock Test 8 that was conducted on 9th of March 2025, and I will be taking the problems of these chapters. The first chapter is System of Particles and Rotational Motion. The second chapter is Moving Charges and Magnetism. Third chapter is Electromagnetic Induction. Fourth is dual nature of radiation and matter, and fifth one is thermal properties of matter, right? Important chapters as far as the NEET examinations is considered, and obviously NEET exam is approaching, so you must keep on watching these sessions where we are discussing the curated problems for you, right? These problems were the problems which were most prone to the mistakes as the students attempted the paper, right? Now, let me start with the first problem, and the first problem is from the chapter of thermal properties of matter. This first problem, it is from the chapter of thermal properties of matter, and the problem is problem 11 of the original paper. It says that the percentage change in length of 1 meter iron rod if its temperature changes by 100 degrees Celsius is. So you need to find the percentage change in length of 1 meter of iron rod if the temperature changes by 100 degrees Celsius, and you have been given the coefficient of thermal expansion as 2 into 10 raised to the power minus 5 per degree Celsius. Okay. So dear students, let me draw the rod for you. So there you go. I have a metal rod with me, right? And let the original length of this rod be L0, right? Let the original length of this rod be L0, and suppose that I start heating this rod. Suppose that I start heating this rod, and this rods expand by a certain amount. It expands by this much part, and this part is delta L. Good morning. So this part is delta L. This much part is expanded, and this part is given by delta L, right? Good morning. So this part is delta L, which rod has expanded, and we need to find what is the value of this delta L, right? And coefficient of thermal expansion of this rod is given to me as alpha. Alpha is alpha is the coefficient of thermal expansion, right? And we need to find this delta L. Now from the, whatever you have studied in the chapter of thermal properties of matter, from there, you know that this delta L, it is given by L0 alpha delta T. This delta L, it is given as L0 alpha delta T. What is L0? L0 is the original length of the metallic bar. Alpha is the coefficient of thermal expansion, and delta T is the amount by which the temperature of the rod is changed. Suppose that the change in the temperature is delta T and original length is L0. So this delta L, whatever the amount of length it will be increased by, it is given by L0 alpha delta T, right? So this new length of the rod, this L prime, what should be the new length of the rod? New length of the rod L prime, it should be equal to L0 plus delta L, right? This should be the new length of the rod after it expanded through a certain part. So this could be written as L0, and in place of delta L, what can I write in place of delta L? I can write L0 alpha delta T. So L prime is L0 plus L0 alpha delta T, right? So if I take L0 as common, so L0, I am taking L0 as common, so it becomes 1 plus alpha delta T, right? So this is the expression that we are going to use. L prime, it is equal to L0 1 plus alpha delta T. Now dear students, the new length, it is given by L0 1 plus alpha delta T. Now here in this problem, you have to find the percentage change in the length of the rod. So the change in the length of the rod, it will be equal to L prime minus L0. This is the change or absolute change. This is the change in the length of rod, right? And relative change will be L prime minus L naught by L naught. This will give you the relative change. And the percentage change, you multiply this factor by 100. So L prime minus L naught divided by L naught, you multiply it by 100, it will give you the relative change. So you need to calculate the value of this part, L prime minus L naught by L naught into 100. Okay. Now let's calculate. So L prime, it is equal to L naught. Okay. So let me do it here. So L prime, it is equal to L naught 1 plus alpha delta T. So if I rearrange this expression, L prime by L naught minus 1 will be equal to alpha delta T. Right? So if I rearrange this, L prime minus L naught by L naught, the relative change, it is coming out to be equal to alpha delta T. You can directly use this expression for your examinations. The relative change is given by alpha delta T. And if it is asked that percentage change, so you multiply this factor by 100. So it becomes alpha delta T into 100, right? So you just need to do this part of calculation. Alpha delta T into 100 will give you the answer. So what is the value of alpha over here? So you can see that the value of alpha is 2 into 10 raised to the power 5. So I'm calculating the value of alpha delta T into 100. So it is equal to 2 into 10 raised to the power minus 5 into delta T is 100 degrees Celsius. So it could be written as 10 raised to the power 2 into 100, again 10 raised to the power 2. So 10 raised to the power minus 5 into 10 raised to the power 4. It becomes, this part, it becomes 2 into 10 raised to the power minus 1, or it could be written as 0.2% is the correct answer to this problem, which is given to me in option 1. So this one is wrong, this one is wrong, and this one is wrong. Right? Okay. Anyone getting the answer? Option 1 is the correct answer to this problem. If you have any doubts, you can put the doubts in your comment box. And if you got the answer, you can also write the answer in the comment box. Yes, 0.2% is the correct answer to this problem. Dear students, if you understood this problem, let's move forward to the next problem. This was a simple problem. You can take the screenshots if you want. And let's move forward to the next problem. And there you go. Next problem is from the chapter of dual nature of radiation and matter. And this was problem 20 of the original paper. Let me go through the problem. So the problem says that monochromatic light of frequency F1 is incident on a photocell and stopping potential is found to be V1. So you have a monochromatic light of frequency F1, it is incident on a photocell, and a stopping potential is found to be V1. What is the new stopping potential of the cell if it is radiated by monochromatic light of frequency F2, right? So dear students, for attempting this numerical, you should know the Einstein equations. So let me assume that the stopping potential is capital V, and this is your stopping potential. Right? I am denoting capital V as stopping potential. Then you have F as the incident frequency. And phi naught is the work function. Right. Now, dear students, the maximum kinetic energy of photoelectrons K max, it is given by, so if F is the incident frequency, so the energy incident will be equal to H into F. So maximum kinetic energy, it will be equal to H into F minus the work function, phi naught. Right? This is the equation we all know. K max, it is equal to H into F minus phi naught. Now this K max, it can also be written as E into V, where V is your stopping potential. So E into V, it will be equal to H into F. So this one is H. So E into V, it is equal to H into F minus phi naught. This is your, again, next equation. So we are going to use this equation to solve the problem. E into V, it is equal to H into F minus phi naught. V is the stopping potential, F is the incident frequency, and phi naught is the work function. This phi naught, it could also be written as Hc by lambda naught. And what is lambda naught? Again, lambda naught is threshold wavelength. So this is the equation that we are going to use to solve the numerical. Now let me solve it for you. So I have the equation EV, it is equal to HF minus phi naught, right? This is my standard equation. Now let me put the data that is given to me in the problem. So I have a monochromatic light of frequency f1 and it is incident on a photocell. Stopping potential is found to be V1. So stopping potential is found to be V1 when the incident frequency was f1. So I will write EV1, it will be equal to HF1 minus phi naught. This is my equation 1. Now for the second case, what is the new stopping potential of the cell? So let me assume that new stopping potential of the cell is V2. I am taking new stopping potential of the cell as V2 if it is radiated by monochromatic light of frequency f2. So if I am assuming new stopping potential as V2, so I can write EV2 to be equal to HF2 minus phi naught. This phi naught is going to remain same because this is the property of the material. So I have two equations, 1 and 2. So from here I can write that EV2 minus HF2, EV2 minus HF2, it is equal to EV1 minus HF1. I wrote this using equation 1 and 2, right? And from here I can write that I need to find the value of new stopping potential, or I need to find the value of V2. I need to find the value of V2, so I can write that EV2 minus EV1, it will be equal to H times of F2 minus F1, right? So if I rearrange this, it becomes V2 minus V1, it is equal to H by E times of F2 minus F1, right? So from here I can write that V2 is coming out to be equal to V1 plus H by E times of F2 minus F1. So there you go, the correct answer is option 1, that is V1 plus H by E, F2 minus F1. Any doubt in this problem? Any doubt? If you have, you can put the doubt in the comment box. Option 1 is the correct answer to this problem, and we use the Einstein's equations. This equation was used, the maximum kinetic energy, it is equal to HF minus phi naught, and maximum kinetic energy itself is written as E into V, where V is the stopping potential. So these are the basic concepts that we use to solve this problem. And we got the answer as option 1. So rest 3 are wrong. Okay. No comment, that means that this concept is clear. Now let's move forward. And if you got this concept, अगर आपको ये concept समझ में आया है, तो you attempt this numerical, and it is right in front of you. There you go. It is an additional question, and okay, a little bit problem is rearranged. The setup is a little bit disturbed. It says that when the metallic surface is illuminated with radiation of wavelength lambda, the stopping potential is V. If the same surface is illuminated with radiation of wavelength 2 lambda, stopping potential is V by 4. You need to find the threshold wavelength for the metallic surface. Okay. So threshold wavelength, I just discussed that if stopping potential is phi naught, it is given by SC by lambda naught, where this lambda is your threshold wavelength. Where this lambda is your threshold wavelength. Right? So for the first case, let me form the equation. So when a metallic surface is illuminated with a radiation of wavelength lambda, so stopping potential is found is V. So I can write EV to be equal to HC by lambda minus phi naught. This is my equation 1 from the first part of the data that is given to me in the problem. Now for the second part, if the same surface is illuminated with radiation of wavelength 2 lambda, so the stopping potential is V by 4. So I can write E times of V by 4. This is the stopping potential when the wavelength is changed to 2 lambda. So SC by 2 lambda minus phi naught. This is my equation 1, this is my equation 2. Right? Okay. So let me write the equation over here. So EV, it was equal to SC by lambda minus phi naught, and EV by 4, it was equal to HC by 2 lambda minus phi naught, and you have to find out the threshold wavelength. Threshold wavelength is what you need to find. Now, let me solve this for you. So I'll put the value of EV from equation 1 into equation 2. I'll put the value of EV from equation 1. EV की value equation 1 से I'll take out and I'll put this in equation 2. So I'll write 1 by 4 times of EV. In place of EV, I'll write SC by lambda minus phi naught. It is equal to HC by 2 lambda minus phi naught. Right? And if you are getting the answer, you can put the answer in the comment box. So if I rearrange this, it becomes HC by 4 lambda minus phi naught over 4. It is equal to HC by 2 lambda minus phi naught. Right? Now we can rearrange this. Let me rearrange it for you. So phi naught will come to this side. Phi naught minus phi naught by 4, it becomes 3 phi naught by 4. And this SC by 4 lambda goes to that side. If I take SC by lambda as common, so it becomes 1 by 2 minus 1 by 4. Right? So from here I can write that 3 phi naught by 4, it is equal to HC by lambda, and 1 by 2 minus 1 by 4 is 1 by 4. Right? So, and 3 by 4, in the place of phi naught, I'll write HC by lambda naught. And lambda naught is my threshold wavelength. So it will be equal to HC by lambda into 1 by 4. So let me cancel this 4 and 4. Let me cancel this HC and SC. So I have 3 by lambda naught to be equal to 1 by lambda. So from here, lambda naught is coming out to be equal to 3 lambda. Yes, someone has given me the answer. Yes, 3 lambda is the correct answer to 3 lambda is your threshold wavelength. Got it? So 3 lambda is the threshold wavelength, and the value of lambda naught is coming out to be equal to 3 lambda. So that's how you deal with such kind of problems. Just using the basic equations, little bit of rearrangement, थोड़ा बहुत rearrangement कीजिए, and if you are good with the rearrangements, you will get to the final answer. So that's how you deal with such problems, and yes, 3 lambda is the correct answer, and you get such problems in the actual NEET examinations also. Yes. Okay, very good. 2 students have got the right answer. Very good. Good morning. Now, if you understood this problem, let's move forward to the next problem, and this problem is from the chapter of Electromagnetic Induction, and problem 28 of the original paper. It's a very short problem. It says that unit of self-inductance is. So this time you need to find the value of self-inductance, the unit of self-inductance, but not the SI unit. You have been given different units, and you need to pick the right unit of the self-inductance from these options. Now this question can be a little bit tricky. So let me do it for you. So self-inductance. In physics, we denote this self-inductance by capital L. And if I need to find different units of self-inductance, I'll take the help of the formulas that I know from the chapter of electromagnetic inductions. Over there, we discuss the concept of self-inductance as well as mutual inductance. So I'll take help of those formulas to get to the units that has been given to me, or I need to check which of the given is correct. So first unit, it takes into consideration the ohm and second. So ohm is somewhat related to resistance, and second is somewhat related to time. So can you recall any formula which contains resistance and time as well as inductance? Any formula, कोई भी formula आपको ऐसा याद है जिसमें you have inductance, you have the resistance, and you have the time. So I remember one such formula, that is tau, time constant of a LR circuit. Time constant of a LR circuit, it is given by tau, that is equal to L over R. Right? Now this time constant, it will have a unit of second. So this is going to have a unit of second, and this is going to have a unit of ohm. So the unit of self-inductance from here, it becomes ohm second. ohm second is the unit, and it is given ohm second square. Ohm second square is given to you, but the unit is coming out to be equal to ohm second. So this one is wrong. Option 1 is wrong. Now let's head to the second. So it is dealing with Weber and ampere. So do you remember any such formulas which includes the magnetic flux, current, as well as the self-inductance? Any formula which links self-inductance, magnetic flux, and current? So yes, I remember one such formula. Phi, the magnetic flux, it is given by L into I. Phi is given as Li. This is one of the formulas that we use, or you use very intensively while dealing with the chapter of electromagnetic induction. So this phi, it will have a unit of Weber. L you need to find, this will have a unit of ampere. So one of the unit from here, it is coming out to be equal to Weber per unit ampere. So Weber per unit ampere, it is given as Weber per unit ampere square. So this one is also wrong. Now let's talk about the third one. So you have volt, second, and ampere. So any formula that deal with EMF, current, time, and the self-inductance. See, phi is given to you. The magnetic flux, it is written as Li. And we know that induced EMF, I'm writing only the magnitude part, it is d phi by dt. So it is written as L into di by dt. Induced EMF can be written as L into di by dt. So this will have a unit of volt, this will have a unit of ampere, and this will have a unit of second. So from here, the unit of L, it can be written as volt second per unit ampere. Volt second per unit ampere, you have been given volt second ampere. So this one is also wrong. This cannot be the correct answer. So if we have nullified 3 options, that means correct answer should be option 4. But obviously we have to derive this also. So dear students, if you have an inductor and if current I flows through the inductor, we know that energy stored, if it is a part of a circuit, it is given as half into L into I square, half Li square. This is also a very famous formula, half Li square. So this will have a unit of joule and this will have a unit of ampere square. So from here, one more unit of self-inductance is joule per ampere square. Let us get through the option. Yes, joule per ampere square is given to you. That means option 4 is the correct answer to this problem. So you see, the problem was very short. Problem seems very simple, but you have to do a little bit of calculation, or not calculation. You have to remember the formulas to get to the correct answer, right? Okay. So dear students, I hope I made this problem clear. If you got any doubt, you can put the doubt in the comment box. Okay, let's move forward. There you go. We are talking about the inductor, and the next problem is again for the inductors. And this time, this is from the chapter of electromagnetic induction, problem 29 of the original paper. It says that 3 inductors are connected as shown. The effective inductance of the network is. So you have to calculate the effective inductance of the network, and obviously you have to ignore the mutual inductance. So you need to ignore the mutual inductance and you need to calculate the effective inductance. So dear students, how to deal with inductors? So when the inductors are connected in series, for the series combination of inductors, okay, for the series combination, suppose I have L1, L2, L3, n number of inductors, they are connected in series. So L effective for the series case, it will be written as L1 plus L2 plus L3 and so on. This is the formula for the series combination of inductors, right? What about the parallel combination? For the parallel combination of inductors, let's talk about the parallel combination. So again, you have L1 inductance L1, L2, L3 up to so on. So in this case 1 over L effective, it will be equal to 1 over L1 plus 1 over L2 plus 1 over L3 and so on. So you can see that these combination of inductors, they are behaving in the same way as you deal with resistors. So when they are in the series combination, you add them up, and when they are in parallel combination, you use this formula 1 over R equivalent, it is equal to 1 over R1 plus 1 over R2. But if we talk about the capacitors, let's talk about the capacitors. So when we are dealing with capacitors, in that case, in series combination, you will use this formula 1 over C equivalent, it is equal to 1 over C1 plus 1 over C2, and for the parallel combination, you use C equivalent, that is equal to C1 plus C2. So that's the basic difference while dealing with inductors and capacitors. So you can remember this for your future reference, that inductors and resistors, they behave in the same manner when they are connected in series or parallel combination, and when you are dealing with capacitor, they work in the reverse manner, right? Okay. So you have the formula for the parallel combination, you have the formula for the series combination. Now the problem is very simple. You have to identify that which inductors they are in parallel and which inductors they are in series. You can use the respective formula to get to the answer. So you have 2 Henry, 3 Henry and 4 Henry. You need to find the effective inductance between point A and B. So from my analysis, I can see that this 2 Henry and this 3 Henry, they are in series combination, right? So I can write that this is point A. So this 2 Henry, 3 Henry, their equivalent, it will be equal to 2 Henry plus 3 Henry, that is equal to 5 Henry, right? So if I draw the equivalent circuit, it will be, this is point B, and this is your 5 Henry, and again you have a 4 Henry like this. Yes, so this is 4 Henry. Now these two inductors, they are in parallel combination over here. Right? They are in parallel combination. So what is the L effective value? See, L effective, it can be written as 1 over L effective. For the two combination, it is written as 1 over L1 plus 1 over L2. So 1 over L effective, it will be equal to L1 plus L2 over L1 L2. So L effective, it will be equal to L1 L2 over L1 plus L2, right? So if I need to calculate the value of L effective, how to calculate the value of L effective? Okay, L1 L2 upon L1 plus L2. So you have 5 into 4 upon 5 plus 4. So 5 into 4 is what? 20, and 5 plus 4 is what? 20 by 9 Henry is the, effective mutual inductance between point A and B. Option 3 is the correct answer. Not option 1, not option 2, not option 4. Option 3 is the correct answer to this problem. Yes, option 3 is the correct answer to this problem. So dear students, I hope you got how to deal with inductors. Just remember that RLC, so resistors and inductors, they behave in the same manner, and capacitor, it will be opposite to what you read or what you use the formulas for the resistors as well as inductors. Now, if you got this, let's move forward to the next problem. And yes, you have problem 30. And you have problem 30, it is from the chapter of Moving Charges and Magnetism. This time they are asking you to comment about the force between two current carrying wires, and this time the current carrying wires, they are in opposite direction. Okay. So let's how to deal with such problems. So this is one of the infinite wire that is carrying current I1, right? And you have another wire and it is carrying current I2, right? And you can see that I have drawn current in the opposite direction. So you can see I1 and I2, they are in opposite direction. And let me assume that these wires are separated by a distance d, right? Now, tell me that if I have a wire I1, infinite wire I1, and if I want to calculate the value of magnetic field at point P, which lies at a distance d. If I want to calculate the magnetic field due to this straight infinite wire carrying current I1 at a point P, which lies at a distance d, what should be the value of magnetic field at this point? Can anyone give me the value of magnetic field at this point? So magnetic field B at this point, it will be equal to mu naught into I1 over 2 pi d. This is the value of, this is the magnitude of the magnetic field, and if you want to calculate the direction, or if you want to know the direction, you can just place your thumb in this direction and the finger curling will give you the direction, so it is into the plane. So you got the magnitude, you got the magnitude as well as you got the direction also. So you are sorted. So first part, so if I want to calculate, suppose that I take a very small segment of this wire, this DL segment, and this lies at a distance d from this wire, right? So what should be the value of magnetic field at this point? It should be mu naught I1 over 2 pi d. Now, see, the magnetic force on a current carrying wire, Fm, it is given by I times of L cross B. This is the next formula that we are going to use. The magnetic force on a current carrying conductor, it is given by I L cross B. So this DL, it will experience a force. This DL, it is carrying current and it is placed in a magnetic field. So definitely this small segment DL, it is going to experience force. Let me write the magnitude. So DF, so it is equal to I DL cross B. So DL, the direction of DL is this and B is into the plane. So DL cross B, the angle between the angle between DL and B, it is 90 degree. So the magnitude will be I. So what is the current in this wire? It is I2. So I2 into DL into B. And what is the value of B? Value of B is this. So I can write DF to be equal to I2 into DL. In place of B, I'll write mu naught I1 over 2 pi d. So force per unit length, dF by dl, it is coming out to be equal to mu naught I1 I2 over 2 pi d. So this is the magnitude, and how to find out the direction. So you just need to do dl cross b. So dl is like this and b is into the plane. So if you do the cross product, it will be like this. So if they are carrying current in the opposite direction, they will repel each other, or they will try to move away from each other, right? And if they are carrying current in the same direction, they will try to attract each other. So had the current be in this direction, so you can see that dl cross b, the force would have been this direction. Currently the force is in this direction. So obviously they are trying to move away from each other, they are trying to repel each other, which means that correct answer should be repel each other. Not attract each other, do not exert any force, no, either repel or attract each other. So just now you got the force. This is the expression for the force per unit length, mu naught I1 I2 upon 2 pi d, right? And they repel each other because they are carrying current in the opposite direction. If they are carrying current in the same direction, they are going to attract each other. And you can find out the direction using the using the concept of cross product, right? So you can take the screenshot, you can note it down in your notebooks, and you can also recall such formulas. These formulas come handy while dealing in the actual examinations. Now, let's move forward. You can also take screenshot of these formulas if you want. Now let's move forward to the next problem. There you go. Okay. And you have a problem 32, and this problem is from the chapter of Moving Charges and Magnetism. So, it says that a charge Q is moving with a velocity v parallel to a magnetic field B. Force on the charge due to magnetic field is. So this time you have to calculate the force on the charge due to magnetic field. So dear students, we have three cases with us. So magnetic force on a charged particle Fm, it is given by Q, that is a charge of the charged particle. Let the velocity be v, so v cross b. So if a charged particle, it enters a magnetic field B, then the magnetic force on the charged particle will be given by the expression Fm, that is equal to qv cross b. Now for this you have three cases. Suppose that for the first case, the angle between V and B, theta, it is equal to 0 degree or 180 degree, right? So if the angle between V cross B, it is 0 degree or 180 degree, in that case, you can see that the magnetic force experienced by the charged particle will be equal to 0. The magnetic field will be 0 because QVB sine theta, either sine 0 or sine 180 will be equal to 0. So magnetic force on the charged particle will be equal to 0, right? It means that particle will pass undeviated. Particle will pass undeviated, or it will continue to move in straight line. Right, this was the first case. Now let me take that if I assume that the angle between V and B is 90 degree. In that case, the magnitude of magnetic force, it will be equal to QVB, and this force, it will be perpendicular to the velocity, because you can see that this magnetic force, it is coming from the cross product of V and B. So it will be perpendicular to both the velocity as well as the magnetic field. So Fm, it is equal to QVB, and this force will be responsible for providing the necessary centripetal acceleration. So for this part, it will move in a circular path. It will move in a circular path, so I can write that QVB, it will be equal to mv square by r. And from here, I can calculate the radius of the circular path, which will be equal to mv by qb. R will be equal to mv by qb. So the particle is moving in a circular path with constant speed. With constant speed is the keyword. And for circular path, the time period will be given by 2 pi m by qb. Right? So the particle is going on with constant speed, which means that the kinetic energy will remain constant, but the momentum and the velocity both are going to change. It will be similar to the case of uniform circular motion. In uniform circular motion, you can see that the speed is constant, but the velocity is continuously changing. So QVB, it is equal to mv square by r, or r is mv by qb. Now, what is third case? Theta, it is not equal to 0, 90 degree or 180 degree. Right? In that case, let me assume that this is V and this is B. So particle is entering a magnetic field where its velocity is making an angle of theta with the magnetic field. So in this case, you have two velocities, one along the magnetic field, V cos theta, and you have one velocity perpendicular to magnetic field, V sin theta. So what happens is that this velocity will be responsible, or this velocity will make the particle undergo circular path. So that radius of circular path, it will be mv perpendicular qb. So mv perpendicular will be mv sin theta by qb. This will be the radius of circular path. Again, time period will be 2 pi m by qb. This will be the time period. And what will be the path of charged particle? It will be helical. So it will be something like this. So it will be a helical path. So you have two velocities, v cos theta over here, and you have v sin theta over here. So this v cos theta, it will be providing the pitch. And what is pitch? Distance traveled along magnetic field in one time period. Right? So if I want to write the pitch will be equal to v cos theta into time, where time will be equal to 2 pi m by qb. So for this case, it will have it will be a helical path with constant pitch. Right? So it will be a helical path with constant pitch. So if you want to take the screenshot, you can take. Or this is the summary of how to deal with the magnetic force that will be applied on a charged particle if it is trying to enter a magnetic field with a certain velocity v. So it depends upon at what angle it is entering into the magnetic field. If angle is theta or 180, no magnetic force will act. It will pass undeviated. It will continue to move in the straight line. If it is 90, the particle will undergo the uniform circular motion. We have the expression for radius, for time period. And from these expressions, you can also find out the expression for the frequency. Again, if neither 90, neither 0 or 180, in that case, you have helix. And for the helix, you need to calculate one additional thing, that is pitch. What is pitch? Distance traveled along magnetic field in one time period. So that's how you deal with such problems. Now let's get back to the original problem. So the problem says that a charge q is moving with a velocity v parallel to a magnetic field b. Force on the charge due to magnetic field is. So it is parallel, which means theta is 0. So in that case, force will be equal to 0. Option 3 is the correct answer to this problem. So this is wrong, and this is also wrong. So this would be the answer if theta would have been equal to 90 degree. Right? Okay. So dear students, I hope this point was clear. Now let's move forward to the next problem. And it was problem 37 from the original paper, again from the chapter of Moving Charges and Magnetism. It says that two similar coils of radius capital R are lying concentrically with their planes at right angles to each other. So you have a plane that are at right angle to each other. The current flowing in them are I and 2I. So you have one of the is carrying current I, one is carrying current 2I. The resultant magnetic field induction at the center will be. So first you need to visualize what is the arrangement given to us. So you have a current carrying coil like this. Suppose that it is carrying current I1, and again you also have a current carrying coil like this, and it is carrying current. So if this is, suppose, let me take this as I. So it is carrying current 2I. So you need to find the resultant magnetic field induction at the center. So at center. So dear students, if you have a circular coil, which is carrying current I1 in this direction and the radius is A. So magnetic field at center, the B. What is the expression for B? What is the expression for B? Expression for B, you can write it as mu naught over 4 pi into I by A, and angle subtended at the center due to this complete coil will be 2 pi. So the value of B, it will be equal to mu naught I over 2A. This will be the expression for the magnetic field at the center. And how to find out the direction? You can curl your finger along this sense, and your thumb will give you the direction, right? So B, it is equal to mu naught I by 2A, right? And if you have a coil, this is I, and if you want to find the field at an axial point P, which lies at a distance of D, and if the radius is A. So you have two kinds of point for a circular coil. You have one axial point as well as one is at the center. For this part, if you want to find the field at this point, B will be equal to mu naught I A square over 2 A square plus D square raised to the power 3 by 2. So just don't be confused with the formulas. One is for the axial point, one is for the field at the center. So B is equal to mu naught I by 2A. That is the formula that we are going to use for this problem. So if you want to write due to this loop 1, so for loop 1, if the radius is R and carrying current is I, so field at the center will be mu naught into I by 2R. And due to this loop 2, again for this loop 2, the field at the center B prime, it will be equal to mu naught. It is carrying current 2I by radius is 2R, right? And you can see that the field due to this loop 1 and loop 2, it will be perpendicular. So they will be something like this. So if, the resultant will be coming something like this, right? So resultant, it will be equal to, okay, let me write the resultant over here only. So I'll take this whole term as alpha. So this whole term will become 2 alpha, right? So resultant will be equal to under the root of alpha square plus 2 alpha whole square, because they are mutually perpendicular to each other. So 2 alpha whole square plus alpha whole square, 4 alpha square plus alpha square, it becomes alpha root 5. Resultant is coming out to be equal to alpha root 5, or root 5 times of alpha. The value of alpha is mu naught I by 2r. So root 5 times mu naught I by 2r is the correct answer, not 2. Not 2, option 4 is the correct answer to this problem. That's why you need to pay the attention in the class. So not 2 is not the correct answer. Had you ticked the answer 2 in the original paper, you would have get the negative marking. So this one is wrong, this one is wrong, this one is wrong. Option 4 is the correct answer to this problem. Yes, option 4 is the correct answer to this problem, right? So you need to remember these formulas, one at the center and one for the axial point. So this formula is not used much, but this will be used very extensively, this formula, right? So you need to remember these formulas. So dear students, with this, I'll end this session. And thank you for watching the video, and keep tuned for more such videos, and all the very best for your examinations. Thank you.